which, yes, you have Lyapunov function, meaning the function we are increasing along the orbits, so that the function is constant on some orbit in on only the point in shell is chain recurrent. This Lyapunov function distinguishes the chain recurrent classes. That is, if you have 2 points which are chain recurrent, they are in the same chain recurrent class if and only they have the same image by the Lyapunov function. And finally, between the image of 2 classes, you always have labels without any chain recurrent point, which allow you to separate the classes by filtration. So that was the announcement. And for the moment, what we have said is some intermediary result, which says that the chain recurrent classes are precisely what you see of your dynamical system if the only tool that you have is the first topological IDs in dynamical system, which is the use of attracting regions. So, in fact, a point is chain recurrent if and only if each time you separate your space in some attracting region and its complement, which is a repelling region, then your point needs to be in the attractor or in the repeller, so in the union of the attractor and the repeller. And the chain recurrent classes in this way of seeing is you look at the 2 points which are chain recurrent, then for any pair of attractor repeller, then your points are in the union, but in which part? So they are in the same chain recurrent class, if only if you cannot put one in the attractor and the other in the repeller. So if one is in the attractor, the other also. I forget to mention the other results that I will use today, is that we also have seen that the set, if you look at, so you have H, homomorphism on the compact metric space, and you look at the set of pairs, attractors, repeller. So this set is at most countable. So that is what I made on Tuesday. So let us start now and see why this theorem is very close to imply this one. For that, we will first, so now we will read the Lyapunov function. So let's start with our metric space, compact metric space. And I have my homomorphism. And I look at a pair of attractor repeller. So this means that there exists some compact set U with, for compact, with H of U in the interior is included in the interior of U, and A is the maximal invariant set in U. R is the maximal invariant set in the complement of Okay.
Second item. Second line.
Thank you. So I have my X. I have my attacker, my repeller. And I have this attacking region U, which is sent inside. So U is this part. Okay, and the dynamic is going down. And with that, you want to build a function which decreases along the orbit. So there is one which is very simple to do. You take, so there exists find 0. So let's make a statement before. Sorry. So lemma proposition. So there exists phi u, so that for any, or let's say phi, from x to r, so that for any x, phi of h of x is less or equal to phi of x, I want that phi of r is equal to 1, phi of a is equal to 0, and phi of h of x is equal to phi of x if and only if x belongs to the attacker union the repeller. So I want some phi here, which will be 0 here, 1 there, so all that go to 1. That will go to 0. And in the middle, it decreases strictly from 1 to 0. And for that, how do you do that? So you will take here h of u. So you choose first by 0 from x to r, so that by 0, indeed, from 0, 1, by 0 of the union, so the complement of x minus u bar is 1. You want that phi 0 of u is of h of u is 0. On that is precisely and you want that if you look at phi 0 of the interior of u minus h of u, you want that it is between 0 and 1 strictly. So that you always can do is adjust topology. You have a metric space, you have two compact sets, which are the complement, the closure of the complement of u. You have the h of u. You have two disjoint compact sets. When you have a compact metric space on the two disjoint compact sets, there always exists a function which is 0 on one of these, 1 on the other, and strictly between 0 and 1 in the middle. It's like that you make part of unit. So if it is a long time ago, you have to recall this very basic part of So you can do that for, so this part between is called a fundamental domain. What means fundamental domain? It means that if you look at the orbit, when they pass once here, next time there are no more there, and they cannot escape to pass in the closure of this part. So here, they just pass once there. And so if you take the closure, you have some orbit pass twice, once on the upper boundary and once in the lower boundary. So mostly the orbit pass exactly once in the place where the phi is between 0 and 1. Only some orbits go directly from 0 to 1. So that is a decreasing function. If you look at phi 0, it is already a decreasing function along the orbits. Because if you are here, you are 1, 1, 1, 1, 1. So either you go directly to 0, so it's decreasing, or you go once in the middle, which is between 0 and 1, and then you go to 0. So anyway, it's decreasing, but not strictly decreasing. So how do you do that for getting strictly decreasing? Okay, so you do the same. So make the same for now, choose phi n in the same way. Phi n from x to 0, 1 with the same property but associated to hn of u. That is, I want that phi of x minus hn of u to the closure will be equal to 1 phi n of hn plus 1 of u is 0 and phi n of the interior of hn of u minus hn plus 1 of u is strictly between 0 and 1. Okay, it's exactly the same, just changing this fundamental domain by, so I have here hn of u, hn plus 1 of u. So for each of these fundamental domain, you choose this function, which is the Lyapunov function, but not strictly decreasing. Now you notice that if you make the sum of two functions which are decreasing along the orbits, it's still decreasing along the orbits. So now you can take, so consider an the positive number so that the sum of the an are equal to 1, so 0 and infinity. And you consider the sum of the phi n from n in z, but not the 0 infinity, sorry, the minus infinity and max plus infinity. So you take a sequence of points, or positive points which converges, so the theory converges, and is equal to 1, and you take the sum of this function. So each of these functions is decreased only when your orbit go from either from your fundamental domain to between, or from here to there, or directly from here to there. Well,
you want summation an here?
Better. Thank you. Okay, so that is this sum is converging uniformly, so that is a continuous function. and it decreases strictly on the orbit. So it's what I announced. That is, yes, this function, if you have any point x, its image is not in the same fundamental domain. So there is at least one of these numbers which will decrease. And so it decreases strictly. Okay. I also announced, not here, but that is X is a manifold. And independently of what is H, you can assume that phi is smooth. So for that, you have to remember that if you have two compact sets in a manifold, two disjoint compact sets, then there is a smooth function which is 0 and 1, one on the other, on which is strictly between 0 and 1 in the complement. So that's once again is what you do when you see partition of unit. So you can assume that the first one, each of these functions pi n are smooth. And now the unique thing you have to do is to choose better your sequence an, so that these sum not only converge uniformly, but also converge uniformly in any topology. So you get at the limit that converge, making a infinite function. So you can get a smooth function, a smooth Lyapunov function like that. Okay. But okay, that is not what the fundamental theorem of dynamical system announced, because here you just are able to separate your attractor from your repeller and nothing else. You just do something which is strictly decreasing out of the union. Okay, is at this place that this lemma was important. So you have a countable family, an at-most countable family of a pair of attractor repeller. So if it is finite, you just take a finite sum of this function and you get what you announced. But if it is not finite, then you know that they are countable. So you have a sequence an Rn is your family of, so R the pair of attractor repeller. So for each of them, you have phi n, which is either continuous or smooth, which is even, maybe I will change the letter. I will put here psi for, because I already use phi n. So let's put some phi n from H to R. So phi n decrease strictly on non chain recurrent out of R of H, constant on R of H, and no, not R, out of An union Rn, and is equal to phi n is equal to 1 on Rn, and phi n equal to 0 on An. So at it is countable, you again can choose a sum of, let's say, Bn phi n, where Bn strictly positive. You need that the sum of the Bn is equal to 1. Okay, so if you make any sum like that, you get a continuous function which will decrease at each point which is not in some of the unions, or these points which are not in the union for some of the attractor repeller are precisely the non-chain recurrent point. So any sum like that, this decrease strictly on the points which are not chain recurrent. But now you have to choose a little bit better the Bn so that you can get the two last items. You want to be sure that 2 points which are not in the same class have different distinct image, and that the image of the point which are chain recurrent don't contain any interval. For that, you choose the Bn which decrease very fast. So let's assume that for any n, the sum of the n plus 1 to infinite of the Bi is less than 1 over 3 Bn. So I ask very fast decreasing. So this ensures that the sum of the next cannot compensate the term Bn. And so you assume like that, and this implies that if x, y are chain recurrent, but there exists n with x in an and y in Rn, then, so let's call that psi of x is indeed strictly less than psi of, no, is distinct than phi of y. So why that? So I take here there exists n, but indeed I take the first one because my pair attractor repeller are indexed by the integers. So I can take the smallest n so that my 2 points are not in the same attractor or in the same repeller. And one is in the attractor, the other in the repeller. Now, each of these functions is either 0 or one of these one. So when before n, the functions are the same, the psi n are the same. When I arrive to n, which is the infimum where they are distinct, the image of this one is 0, the image of this one is 1. But I have this coefficient Bn, so the difference up to now was for Bn, and what happened after is smaller than 1/3 of this difference, so it cannot compensate. So the gap between them will remain larger than 2/3 of Bn, making that the image are different with a given gap. Okay, so that gives you the two items. I know I have been a little bit fast, but that is, I think, truly easy to make the details. Okay, so I guess I proved all what I wanted to prove about Conley's theorem. I said, you have to check, but that is truly not difficult. That means only that the Bn are decreasing fast enough. So you can make them to decrease faster so that not only this sum converge uniformly, but also in the C-infinite norm, if you want C-infinite Lyapunov functions. So with that, you can build, so you just have to add a faster decreasing for getting that psi can be smooth. If each of your psi n was smooth. Okay. So that gives you a smooth function. So phi smooth n manifold. Okay. So I like very much to teach this theorem because I think it's not so well known, and you can do all the details of the proof, and you see in 1 hour and a half, more or less, or maybe 2 hours. So let me continue a little bit about this subject. What I want to say. So, okay. So maybe first, people are also interested in flow. So I will not say so much. So let's say smooth flow on a manifold, or P1 flow on a manifold, and you want to get a Lyapunov function associated to the chain recurrent set. So the chain recurrent set consists in points that you can close by pseudo-orbit. Pseudo-orbit are interval of your flow. So the pseudo-orbit are, you have a point, you follow a time larger, t0 larger than 1, or equal to 1, then you allow a jump of epsilon, then you follow a time t1 larger or equal to 1, and so on. And like that, you get your pseudo-orbit. This defines the notion of chain recurrent set for your flow. You have the chain recurrent classes in the same way, and you would like to get Lyapunov function for your flow. And so you have to check that this notion of chain recurrent for the flow is exactly the same as the chain recurrent set for the time 1 of the flow. So when you do that, you can apply the Connelly theorem, getting your Lyapunov function for the time 1 of the flow. And so that decrease along the orbit, mostly if you take enough time. So if you want to get true decreasing along the orbit, what you do is you make an integration of the Lyapunov function for the time 1 of the flow on segments of size, let's say 2. Then, if you look at the derivative, you get the difference between your function at time t and time t plus 2, which is strictly negative. So you get that your function is strictly decreasing along your orbit if there are not chain recurrent. So it's truly easy to do that. So for flow, you just consider, so phi Lyapunov function for H, which is the time 1 map of your flow. X is your flow. So you look at its time M1, and you look at the Lyapunov function for its time 1, and now you look at, to a point, you associate the integral of phi of xt of x dt from -1 to 1. And let's say 1/2 if you want that it to go from 0 to 1. So you get this one, and the derivative is strictly negative. Its x is not chain recurrent. So, so that gives for flows. Let's see what okay. So I guess that for people doing topological dynamics, it's clear that chain recurrence and chain recurrent classes are important tools. But for those making smooth dynamical system or analytic and so on, maybe it's not so clear. So let's first give some result which shows that the notion of chain recurrent set is important. So I guess that the first time you have seen the notion of axiom A plus no cycle condition, you thought that it's a little bit a strange definition. So you have first to understand the non-wandering set. Then when you understand this non-wandering set, you have to say, yes, but it can be parabolic, but not being the closure of the periodic orbit. And so yeah, now if someone here knows one example of this situation, you are better than me because I have seen once. I know it exists. Someone make an example. This example is truly tricky, but okay, there is an example of a diffeomorphism having a non-wandering set which is hyperbolic, but which is not the closure of periodic orbits. Okay, so you have to add the hypothesis because there is an example which do not satisfy that. And then you say, yes, the no cycle condition. Oh, what means? So you have to look at Smith decomposition theorem and to understand what means no cycle condition. So, okay. So let's notice that theorem. A diffeomorphism, so you have a manifold L and F, a diffeomorphism. Different, also M, a closed manifold. Okay, so then F satisfies the axiom A plus the no cycle condition. This if and only if R of F is hyperbolic. And so you know that this is a characterization of structural stability, C1 structural stability on, let's say, the non-wandering set of F, but also on the chain recurrent set of F, which contains the non-wandering set of F. Okay. So you see, this is a little bit difficult notion of axiom A plus no cycle condition is indeed a very natural condition because it's only the hyperbolicity of the chain recurrent set. But it has not been known for a long time because it's not at all evident. This uses strong tools. So this uses so put some of the tools. So certainly it uses the allosort clothing lemma. The shadowing lemma, the clothing lemma, and a stronger version, which is the Hayashi connecting lemma. And the stronger version, which is my version with Prodizier of the Hayashi coding lemma, connecting lemma. So that are each of them very technical tools and very strong. I will not have any time for explaining that. But just say that at the end, yes, the chain recurrent set is a good notion for defining the structural stability. Is just to be hyperbolic. Maybe if you have in mind what is a cycle in the axiom A theory. That is, you have these basic pieces of the space that define the smell, but you have some point going from one piece to another, and so on, in a cycle. That is a cycle. Well, if you look at in terms of the pseudo-orbit, all your cycle is a unique chain recurrent class. It's contained in a unique chain recurrent class, because from in one piece you can go everywhere by orbit or pseudo-orbits. Then you can make a jump in the orbit going from one piece to another, and so on. So for that, if you assume this one is hyperbolic, this makes that you cannot have cycles, because you have your chain class which is hyperbolic, and therefore it's a unique of this class of the axiom A. So this one implies no cycle condition that is easy. The rest is complicated. So another way to see that it can be useful for other people to look at this notion. So let me, oh yes, also. On Tuesday, I do not remember who asked me if there was infinitely many or uncountably many classes, when I just said that the classes are defined by pairs of attractors repellers, and that these pairs are at most countable. Okay, so let me show you a small things. So let's consider now the situation of smooth or analytic, I guess algebraic are possible also, diffeomorphisms on the plane, on typically the Hénon family. I think that there are people here interested somewhat in Hénon family. So look at the Hénon family. So in the Hénon family, you have some hyperbolic sets. On this hyperbolic set, on some parameters, display an homoclinic tangency. So what is an homoclinic tangency? Is that you have an hyperbolic saddle. So it may have transverse intersection. So let's assume you already have transverse intersection. But let's say that at some moment you have some tangency. So let F from R2 to R2, let's say, or well, from S to S, a surface, and you assume that you get an homoclinic tangency. F display homoclinic tangency. So what happens when you move, you change a little bit your diffeomorphism, either by considering one parameter family so that these unstable manifold move smoothly, or you take some open set and you make any perturbation, but I want to make a continuous family of deformation. I prefer deformation for the moment than perturbation. Okay, the first thing that happened is that if you consider by smooth perturbation, what you can make is you can look at what's happened to some small rectangle. So indeed, I will assume here that the derivative, so the determinant of the derivative of df at my point, let's say P, I would prefer that it will less than 1 or larger than 1, but not equal to 1. So you look at some rectangle. For looking better, I will take a bigger rectangle, but you have to think indeed that it is very, very, very small. And so you consider what happened when it arrives there, so it will be much higher and much thinner, and as you have that, it will be very thin when it starts to be high. And so when it goes back, maybe I should have made a tangent in the other direction, so maybe I will put it like that. I prefer to see like that. So, and we'll see this rectangle coming back in itself like that. So maybe I have to put in red to put some color is this size. Go here and here, and the other, the vertical one, are the very large one here. Okay, but when you start to move your unstable manifold, what you get is a rectangle with this rectangle inside, which move from the bottom to the top. And in the middle, so each time you have that, you have fixed point there, and you get a fixed point displaying an homoclinic tangency. Okay, so starting from one point displaying an homoclinic tangency, you get an attracting region where you see your point displaying an homoclinic tangency. At the same time, this point continues displaying other homoclinic tangency. So you create, in the meantime that you have this family having an attracting region, you create another attracting region having your rectangle crossing and creating a new point with a homoclinic tangency. So starting with one, you get at least two small regions displaying simultaneously homoclinic tangencies. Each of them display two small regions attracting with some homoclinic tangency, and you continue like that. So when you have, so you always have somewhere in your parameters, so you start with something like that, and then from one you get two rectangles with some point having some attracting region. On each side, you see a homoclinic tangency. So you get one, another, and they are disjoint, periodic, of very large period, very small size, but they display each of them a homoclinic tangency. So this one, when you perform you continue moving the parameters, you get smaller region with homoclinic tangency. So from 2, you come to 4. From 4, you go to 8, and so on. Just moving the parameter. And now, so indeed, if you have this, so you know when you have a tangency, you have open set of parameters when you display tangencies in the hyperbolic set, and densely on the periodic point. And so densely in the parameter, you get these breaking the dynamic in 2 p's and in 4 p's and so on. So in your open set of parameters, when you see homoclinic tangency, you have densely more than 8 attracting regions, more than any power of 2 attracting regions. So generically, you have infinitely of these nested sequences of attracting regions. So I'm making here a tree of attracting regions that are nested. And what's happened if you look at the intersections of a nested sequence, so you just choose the branch here of your tree and you follow it. So what you see is the following. You see a periodic region. And when you go back, when you arrive, you see here the periodic region for the return map. That is, this region goes there, which goes there, which goes there, which goes there. When we go back, it goes here and makes the one turn, and then goes there, and so on. And in each of these, so if I look at this one, I see once again a periodic attracting region, and so on. If you make the intersection of that, you get a minimal set, which is a chain recurrent class. Why is that? Because it has a nested sequence of attracting region. It is a maximally invariant set in a nested sequence of attracting region, and it is an adding machine. So you get, like that, you get adding machines, odometros for people. I don't know if you know what are adding machines. Okay, but they are all they are uniquely ergodic and so on. But how many branches you have here? It's a tree. So you have finite branches, you have finitely many. But infinite branches, you have uncountably many. So what is said here is, for example, in the Enon family, you have parameters, but you have generic parameters in one parameter family for which they have uncountably many chain recurrent classes, which are all these adding machines. Okay? So let's say if you take, for example, you take a new house region, new house region, meaning that is a C2 open set of diffeomorphism having tangency between the stable manifold of some compact set on its unstable manifold, where K is an offshore. Well, it's a hyperbolic basic set. Okay, so you take some C2 open region, then C2 generically, or you put CR, R larger than 2, CR generically. You have that F has an uncountable set of chain recurrent class which are all adding machines. So for not being too abstract, and I know that there are students, there are someone who don't know what is an adding machine? Yes, there is someone, so that is important to say. So you know that product of compact set are compact. So look at Z over A0Z times Z over AN Z and so on, where AN are any positive integer. So that is a compact set. Point here is some infinite sequence x0, x1, and so on. And now you will put dynamics which consist in you add 1 here. So you transform that in x0 plus 1, so on. Just that, if you arrive, so if x0 is different from a0, you make x0 plus 1, but if x0, no, a0 minus 1, sorry, if x0 is a0 minus 1, so the image will be 0, x1 plus 1. If x1 is not, I say, a1 minus 1, if it is a1 minus 1, then you put 0 and you get plus 1, and so on. That's exactly what you do with integer when at the school you make plus 1. That is, when it goes up to 9, you have to go to the next number, the f digit, and to add 1. For that, it is the adding machine. So on this compact set, this is a uniquely ergodic dynamics. On all that, I didn't put, I erased my picture, but the plus 1 consists in, that is the first digit, and you make plus 1. And when you arrive there, to the back, then you have the second digit. You look at the second digit and you have to make plus 1. Okay? So that is.
Take a break.
Okay.
Yeah. So 10 minutes.
Let's continue. I think I cannot stop speaking on that without some word on generic homeomorphism. Manifold, closed manifold. So first of all, I have to say that I'm not specialist on generic homeomorphisms, but so there is a book by Atkins, on Kennedy. I didn't put the detail, but I think it's early 21st century, so 2000 and something. But let's just give a result that you can, that it's easy to convince yourself on. So I will put theorem. So the manifold is dimension. It starts in dimension larger than 2. So in dimension 1, I guess you know what is the situation.
Even larger or equal?
So, no, theorem. I will take a smooth closed manifold. And so you can check that there exists some residual subset of numero of M. So if you have F in this, so F generic, F in this residual subset, then you have uncountably many recurrent class which are adding machine. And there are bands, the union of this class are dense in the chain recurrent set. So the chain recurrence set, any point is accumulated by infinitely many of these adding machines. And so the proof of that is pretty easy. That is, you look at, first of all, you have to convince yourself that the closing lemma, that is, you have a recurrent orbit, and you say, I can make a perturbation so that it will be a closed orbit. So the C0 closing lemma is not that complicated. That is, you take your orbit, you choose any moment it comes back. You don't care if it has been back before or not, but you take a small disk containing the initial point, the last point, on no other point of your orbit, and you will make a composition by an homomorphism, which is identity out of this disk, on which send this point there. And so you did not change at all the segment of orbit until there, and you close your orbit. Exactly in the same way, you can check that if you have a pseudo orbit by an epsilon by a small perturbation, you can get a new homomorphism so that your pseudo orbit become a true orbit for the perturbation. So connecting lemma, closing lemma are pretty easy in for homomorphisms. They are not big deal for that. So with that, you quickly get that your chain recurrence set is a closure of periodic orbit for generic homomorphisms. But now, when you have a fixed point or a very fixed point, so you have your point that your homomorphism on itself, okay, take some neighborhood of it, then, sorry, good one. You send in something which is complicated, but there is an homomorphism which sends this complicated thing on the initial one, keeping your fixed point or making it an attracting region. So now you can assume, in fact, by composition, you can make that your fixed point will be identity in the neighborhood. So for homomorphism, each time you have a periodic point, you can assume that the return is the identity. That is not generic because it's fragile. You cannot make open set like that, but you can densely, often by small perturbation, you have your point to say, oh yes, I want that my map is identity in the neighborhood, that you can do. When you have that, you can now take by small perturbation, so you put here a small rotation and you create a very long periodic and attracting region. And you get a fixed point inside that you make the identity for the return map and you create a new one. And so you create these adding machines. So you see that is not a big deal. It's more a big deal. So I'm not telling that that is easy because there are very precise description of the dynamic of generic homomorphisms. So I recommend you to have this book if you are interested by generic homomorphisms. I just wanted to say this result because that is too easy. Also, before ending the Conley theory on the Lyapunov function, I wanted to speak about some open question on that field. So one open question, one still open question. So indeed, then you asked me this question just 10 minutes ago, but okay, I wanted to speak about that. If you take, so let's say that F is a diffeomorphism. You know that there exists psi which are smooth Lyapunov function like in the theorem of Conley. So can it be Morse? Can you choose psi to be Morse function? Okay, so that is easy to, so because the theorem of Conley say most, in some sense, that any dynamical systems look like some gradient of some function, of some smooth function. So can you take this function to be of a Morse function? So you have to look first that if you have a periodic saddle, hyperbolic periodic saddle, it has to be, so it's a periodic point, so your dynamic is constant there, but the fact that you have the stable and the unstable manifold, which are transverse, will imply that your function has a critical point on these saddle points. So if you have range on that, so your function has to be decreasing that direction, but also this one, that is the derivative of your psi has to be 0 in that direction, and has to be 0 in that direction, as the sum of stable and unstable is the whole space, you get that your function has a 0 derivative at this saddle point. So if you have infinitely many saddle periodic orbits, you have infinitely many critical points, so you cannot be Morse. So this question has only, so the question, you only if your dynamic F is at finitely many periodic orbits, at finitely many hyperbolic periodic orbits. Hyperbolic periodic points. Well, but now if you have finitely many, and if it is you want an open set, so a good setting would be F Morse-Mail. So in this setting, the answer is yes. Psi can be of Morse type, a Morse function. But when you have a Morse function, you would like to know what are the critical points. So maybe you can, so there is a terminology that I don't understand very well, but we say that psi is an energy function. If the critical point of psi are equal to the periodic point of F. So you have specific Morse-Mail diffeomorphism for which you have energy function that is Lyapunov function, which are of Morse type and with critical points only on the periodic points. Are there always the case that does any Morse-Mail diffeomorphism have an energy function? The answer is no, and it has been created by Pixton. And so it's true in dimension 2. So in dim equal 2, there exist energy functions. But in dimension 3, so Pixton makes a diffeomorphism on the sphere S3, with no energy function. And this diffeomorphism looks very simple. It has two repellers, two fixed repellers, hyperbolic repellers, one fixed, so two sources, one sink, and one saddle. And what's the trick? The trick, so the separatrices are coming directly from here, but the other here make a complicated picture, which is an activity invariant. When you start to be knotted, you have to be infinitely knotted. And indeed, here the picture is not correct, but because that is knotted with the other, and this one continue being knotted, or it go to the. So you have a diffeomorphism on S3 having one wild knot that is a segment. The separatrices, if you compactify by the repelling point, you cannot rectify this segment. In particular, the fundamental group of the complement of this segment is not trivial. That's some strange object. I classified this kind of object with the grains. So with greenness, we chose that each of these kind of diffeomorphisms with 4 fixed points, or which are Morse-Male, are classified by just a node. And so now there are people we try to answer to the question. So all these with one knotted separatrice do not admit any energy function. So you can ask how many critical points you have to add to the periodic, and that gives you an invariant of the node. And so in this direction, I can mention the work of people around Poshinka. So she has several collaborators with several results of evaluating the number of critical points you have to add to your periodic set for getting a Morse function for your Morse-Male diffeomorphism. Okay. I think I finished what I wanted to say in this. Yeah, so now we change the subject. So questions, a good moment if you have questions on this subject.
Can you explain that example again?
Oh yeah, that's that indeed. We recover this diffeomorphism and we make the classification with a completely different question in mind. Yeah, in mind the classification. And Greenes told me, can we at least classify the Morse-Male diffeomorphism on the sphere with only 4 fixed points, 2 repeller, 1 attractor, and okay, so you start with the north-south dynamics. So you go from here to there directly, so that is F0 is a north-south dynamic. So everybody going straight. And now you choose the fundamental domain. So yes, if you take the quotient, you remove n, you remove s, and you take the quotient. So you S3 minus north-south and quotiented by your F0 is just S2 times S1. So S2 times S1, so you have S2 times S1. And here, you choose a node. You choose a circle homotopic to S1, but not isotopic. So you can make, it's not so easy. So you have, let's say, 3 points here, and we take going that one. And then I can make a mistake, so I did not prepare that. So that has 2 points. I need, yes, I forget this one. Maybe that, I do not remember. I guess here it's making two turn one direction, one turn the other, so it's a motopic to the circle, and that is noted. So there are notes in S2 times S1 on motopic to the circle, and when you look at the lift here, what you get is some invariant curve, which is noted to itself, but as all things here, which go from north to south. So it's something invariant by translation, but which is noted. Now you take a tubular neighborhood of that. So you have a tubular neighborhood where the dynamic is just a translation. So indeed, you look at that which is noted, but what you see inside is just translation or something like that. And here you put that dynamic. Everybody going down. So inside you don't, or at the boundary you don't change anything, but inside you introduce a new fixed point, two new fixed points, one saddle on one repeller. And you take that and you put here, like that, and you get pure diffeomorphism. So it's an easy construction. It's some surgery, but an easy surgery. It's more tricky than complicated. Other question? So if no, I go to the next subject. So I have to think about what I can do in very. I didn't remember how I have until what?
15 minutes, I think.
Fish.
We started a little bit later, so maybe like past 11.
5 past 11. So I have 15 minutes for speaking about the main subject of this course, which continue in May. But let me give you just so an hint about what I can. So I will assume, and certainly it's not the case, and I apologize, that everybody know all about hyperbolic theory. That is, you know what are hyperbolic basic sets, you know that they are structurally stable, you know the invariant manifold stable and unstable, and so on. I will assume you know that. But something that few people have seen is an open set of non-hyperbolic diffeomorphisms. So in the C2 case, people have seen in the Hénon family or in when you display homoclinic tangency, they have seen C2 open subset of diffeomorphism on surface where you know that it is not hyperbolic. But C1, so first the question, there is a still open question, does it exist? A C1 open subset of D2 relative one of surfaces when F is a closed surface, which are not action R. So not F, R of F hyperbolic. That is, I guess, the main question on surface. But in higher dimension, it's very visible and not so complicated to make open set, and much simpler than Neuhaus domains. Neuhaus domains, okay, you have to know what are fractal dimension, and to believe that manifold, when they move, this fractal dimension vary continuously and something like that. It's not that complicated, but it's not elementary. When getting C1 open set of non-hyperbolic diffeomorphism in dimension 3 is very simple. So let me show you that. So if you know hyperbolic theory. So in the hyperbolic theory, you can have hyperbolic attractors, which are saddle attractor. That is, every point is not an attracting point, but the global set is an attracting set. You can do that on surfaces. The most well-known are the derived from anosoph. You take an anosoph diffeomorphism of the torus given by an hyperbolic automorphism of the torus, and you open some unstable direction, and you create a periodic repeller, and you get an hyperbolic attractor. That's very nice. I can make with that, but it's more difficult to draw than another very well-known hyperbolic attractor, which is called Plitkin attractor. So let me draw you a Plitkin attractor. So the Plitkin attractor is an attractor. I like to draw it with 4 rectangles. So you take this picture where you see that is a rectangle, but not a geometric rectangle, a topological rectangle. So you take 4 rectangles like that, and then I have to draw the image of these 4 rectangles. So let's see, for instance, there are many possibilities, but take this rectangle and I will draw it. Like this rectangle, I want to put here. Yes, this rectangle, I put it here. Next rectangle. So it starts with these 2 feet, so I can put here. Then I have to take the image of this rectangle there. So take, for example, this one. This one, so its image goes just there, so it comes here, and you make it like that. On the last one, the yellow one. So it will be truly thin. Maybe I will just make as a segment. It will be easier to draw. You make like that. Okay. What you have to see is that each rectangle has been, you make a contraction in the, what is in this foliation. So this foliation is uniformly contracted, and the other is uniformly expanded. So you get a region going inside itself, but with a completely hyperbolic behavior. So that is an hyperbolic attractor. So the nice thing with hyperbolicity is that it is stable. So I will look at the diffeomorphism in dimension 3, and I will consider a plane, which is invariant. So for the moment, I put my plane here, I put here. So here the maximal invariant set is a lamination that I will draw something like that. So you have to believe that represents my Plitkin attractor. So this Plitkin attractor has saddles in its boundary. There is a repelling set at the infinity, and there are periodic 3 periodical repelling orbit inside the small disk there. Okay, so here you have the repelling set, but all that is a stable manifold of your Plitkin attractor. Let's call it A. Okay, so that is the dynamic on a plane, and this plane is on your 3 manifold. I can make a very strong transverse expansion. So I can add here a very strong normal expansion. And what creates that is that your set, which was an attractor in this plane, is no more an attractor. Now it's a saddle, because it has a non-stable manifold going fully out. And if you look at the unstable manifold, there are something like that. So if I make a cut here, I will see the same picture as below, but like that. Okay, on all this plane is foliated by the stable manifold of the point here. So you have the stable manifold making the foliation there. So all this plane, so each point is stable manifold as dimension 1, but the union of this stable manifold make equal to that plane. Okay? Now, in my dynamic, I can have another locally invariant plane. Here, so this unstable manifold will cut a plane where I have a periodic point whose stable manifold is dimension 2, and its unstable is dimension 1, and cut here transversally. Okay, that's it. That is an open set of non-hyperbolic diffeomorphisms. Why that? Okay, here's the point. You have a splitting, hyperbolic splitting, which is a stable of dimension 1 plus an unstable of dimension 2. Here you have a stable of dimension 2 plus a 1 of dimension 1. But they are connected. And they are robustly connected. Why robustly? The important thing in hyperbolic dynamics is when you make perturbation, stable manifold are moving continuously with your dynamics. So this unstable lamination will move a little bit, but will still cross transversely this plane. On this one-dimensional unstable manifold will still cut transversely this foliated plane. Okay, so here you have that. You will have recurrence orbit between these, going from this situation to that one, to this one, to that one, and so on. And if you continue, 5 minutes for making something which is not so easy to explain to students in dimension 2, robust tangencies. So you have this one, you iterate. This one go by the lambda lemma to that, and then go back there. So let's make the picture again. So you have your splitting attractor, you avoid splitting attractor, and so on. It's unstable manifold, so that it's stable manifold of your splitting attractor. And what you do is, okay, either you just follow this one and go there, or you go directly, making that the unstable manifold cuts again here. So the holonomy draw you here a copy of your splitting attractor by holonomy, so it's maybe not smooth, I don't care. But here, what I know is that it is foliated. On this transverse intersection here is the lamination. You have a lamination in the compact part of a foliated foliation. You always have tangencies. So here, you cannot make the picture with no tangency between, so here I have one, here I have one, and so on. You have plenty of tangencies between your hyperbolic set, which is your old picking attractor, which is now saddle set, with its stable manifold. You have a robust tangency, which it's robust in the C1 topology. Okay? So now you have open set of non-hyperbolic dynamical systems. And let me just give you a small result, going further, a little bit more complicated. take this one and take some periodic point here inside. So you have some hyperbolic saddle somewhere. There are dents in your clicking attractor. So this point has a stable manifold of dimension 1 and an unstable of dimension 2. And for the moment, with my construction, it has a strong unstable and a weak unstable. Okay, change that a little bit and make that this point now has a complex unstable eigenvalue. So you make a perturbation, you make rotated it. Okay, this one is no more smooth, but you still have topological transversality. So, the stable manifold here continue to be a topological surface, which is topologically, at least you have some transversal points. You still have tangencies on the foliation, but you have something more that you broke the strong unstable direction. So here you have, in the 1 minute and a half that I still have, I have some recurrent class. Class, let's say this point is P of P is P1 robustly with no dominated splitting. With no dominated splitting. This means that in the class, you don't have anymore any stable direction, any unstable direction, any direction that you can say this direction expand more than the others. And when you have a class like that, I have to put, I should have to make other things, but I will not be able to have the time. You can create open set where generic diffeomorphisms are what we call universal dynamics. What means universal? It means that take the disk, the 3 disk here, and choose any diffeomorphism on the disk. Your generic diffeomorphism already have a trapping region. Then if you look at the return, and if you make an homothétie for getting a big ball, what you see is something which is as close as you want to your diffeomorphism that you choose. In some sense, so what we get is any generic diffeomorphism in this C1 open set admit infinitely many regions we come periodically, and where you look at them and you make an homothétie, and you look at all the collection you get a dense subset in the set of diffeomorphism on the board. So this kind of diffeomorphism display all the difficult behaviors that you can imagine. So in some sense, they are the worst. Each time you have something a little bit persistent, these diffeomorphisms already have it. So what's happened next is that for forbidding to have this universal dynamic, you need some dominated splitting. You need an hyperbolic structure. Each time you can make something with with robustly no dominated splitting, you get the worst possible. On this one, you create by very simple bifurcations, heteroclinic cycles and so on, with very few, the behavior of 3 or 4 orbits. You have if 4 orbits are in that position, you have this domain. You have the worst. So you have to forbid bifurcation. You need structure for that. But dominated splitting are more or less given by the dimension of the bundles on the what is the behavior in each bundle. So you have finitely many. And with that, I made, I think 10 or 15 years ago, a paper trying to make a complete description of a open set of diffeomorphism, of the dynamic of diffeomorphism in any dimension. It's a program with conjectures, but based on the fact that if you want to avoid the worst, which has everything, you need already a big structure. On structure, you don't have so much choice. So you have a list of structure which break your set of all diffeomorphisms in different regions. Each of them has some specific dynamics. Okay, I think I finished.
Thank you. It's time for questions.
So you said what we find on these disks is a dense set, collection of diffeomorphism of the ball. You don't get every one dead on. You just get a dense set in the straight field. There is a ball.
Yes, you can also have, if you take any countable family of residual subset, you can have one in each of these residual subsets. So you can have a little bit more than only density. You can prescribe to be in some residual subset. But yes, it's using intersection and then open subset, so we cannot have everybody. You need.
Any more questions? If no, let us thank the speaker again. And we start again at 11:30.